Hello everybody, today I'm spending a little bit of time on the traveling salesman problem. This again is another optimization problem that is extremely popular among operation research, and it's another problem in the family of network problems such as the shortest path we talked about earlier. Let's try to think a little bit about the problem, right? We have a network that is made out of different nodes, as you can see, and the main idea of the traveling salesman is that he or she needs to visit every node only one time, and he can or she cannot return to the same node multiple times, right? So each node needs to be visited at least and at most one time. So I'm just going to take another chalk, right? And to show you here, if this is the starting node, and that's important, starting node can dictate then the path, right? How could I do this? So maybe, you know, one way would be to do like this and then go like this one. Of course, you need to minimize the cost, right? Think about this, right? So you could go this way, for instance, and you can possibly go this way. No, you would go this way, and then maybe this way here, and maybe this way, and then back this way. Okay, so this would be kind of a one solution. No, it's possible you go back to the same node and then leave it again, right? I mean, you may, but that's kind of redundant, right? As I mentioned earlier, you're typically not allowed to go back to the same node because you would visit twice, okay? And this type of problem, the traveling salesman problem, is very, it's actually quite important. Companies like UPS or FedEx may use it. Now, in this particular case, like UPS or FedEx or DHL and others, what happened is that each node is actually not really a customer. A node could be a neighborhood, right? For instance, a neighborhood or a township, and UPS goes from one neighborhood and then deliver to the different people there, and then to another neighborhood and then deliver to the other people there. So our objective in the traveling salesman problem, again, visit everyone only one time and minimize the total cost. Now you can see here that this is actually a really complicated problem, and it's as a combinatorial explosion. So let's take a simple example. We have A, B, and C, right? And let's say we don't care about where we start. So if that's the case, the route you can have is A, B, and C. You can have A, C, and B. You can have B, A, C, B, C, A, C, A, B, and so on and so forth, right? Excuse me. So you do have a lot of options. Now, if you decide that you want to start in A and end in C, okay, then you only have one option. That's pretty straightforward, and that actually reduces a little bit. But if you do not know that, where you start and where you end, then you have essentially a problem of the order of n exponent here. I mean, a factorial, sorry, and that of course leads to a lot of combinations. So for this example, right, we would have 3 times 2 times 1, and that is equal to 6 different possibilities, as you see right here. I'm going to now show you the formulation for this problem. Alright, I'd like to spend a little time on the formulation of the traveling salesman problem. It's actually not so much different from the shortest path problem, but remember the objective is to visit every city one time, avoiding this sort of cycling, which will be taken care of by some new variable. So the decision variable xij always the same. If a path goes from city I to j, 0 otherwise, right? So basically if we traverse that path, cij the cost to traverse that link ij. And our objective function is a minimization of the cost, similar to the shortest path problem here. There are a couple of a new variable here, and one new variable u sub I that is introduced, which is dummy variable. We'll talk about this in a second. And this one here is basically to say xij is between 0 and 1, or we could have essentially said that every link is either 0 or 1. So that's when they are selected in the system, yes, on the route, sorry. Those two are kind of similar to what we saw in the shortest path. Not quite the same, but it basically says here for this one that each city is arrived from exactly one other city, but that other city cannot be I, okay? So you have to come from another city. And then here this is the same, but basically it says each city is departed from exactly one other city. And again, I and j's are different. Now, what about the last two variables here, and the last two constraints? And those are very important. So we're going to use a new variable, decision variable. It's actually a dummy variable. And this is going to actually avoid that we are going to cycle multiple times through the system, because that's possible. I mean, especially if you have a link that maybe is, you know, either 0 or maybe negative. I mean, it can happen. But how do we avoid that we cycle? How do we avoid that, for instance, right, if I have here a network, right, how do we avoid that, you know, we go in here like this, like this, like this, like this, like this, like this. How do we avoid this multiple cycle? And these two constraints here are just going to take care of that. So essentially they allow you to do one cycle and no more than one cycle. So I'm not going to show example in Cplex for this one, but I will definitely show some example within a GIS environment to better illustrate the mechanism of this problem.